So in our previous videos on derivatives, a derivative is essentially just the rate of change for a given function. And for a nonlinear function, it helps for us to think about tangent lines and their slopes to visualize what the derivative would be. Now, we also found a way using algebra to determine what the slope of the tangent line would be. But this is extremely tedious and additionally doesn't always give us as much information as we want. Often in economics, we want to find f prime x, which is a function determined using f of x by taking the derivative of f of x. And f prime x will give us a way in which we can graph the derivative. And it also gives us a means by which we can plug in some value of x and find out what the derivative would be at a given value of x. So in this video, we're going to be looking at two different types of functions that we see often in economics and how to take their derivatives. The first is polynomials, and we have a polynomial here. What distinguishes a polynomial from other functions are these exponent terms. So we have an exponent term here, for example. The example we're evaluating is 5x cubed plus 2x plus 1 is equal to y, which is a function of x. And below, we have a nice graph that shows us how this function behaves. As you can see down here, it's increasing, but it's increasing at a decreasing rate, which explains this curve right here. So with every increase in x, y increases by smaller and smaller and smaller amounts. We see the opposite here. For each increase in x, y will increase by greater and greater and greater amounts as the curve starts to move like that. So how do we take this derivative? Well, with polynomials, you really have to think about how do I take the derivative when there's exponential terms. And there's a couple of very, very straightforward rules for doing so. So if we take first, we look at right here, this first term. The general rule is that you move the value of the exponent down, multiply it by whatever constant there is there, and then you change the exponent such that it becomes whatever the exponent is minus 1. Hence, if we want to write out the first piece of the polynomial derivative here, we'll get f prime x is equal to 5 times 3 times x to the 3 minus 1, which is 2. So it's 5 times 3 times x squared. Now let's take a look at this next piece. Now, you may have seen before that 2x would be equivalent to 2x raised to the first power. This is because, remember, the power tells us how many x's we're multiplying by. So x cubed is x times x times x, whereas x is just, you're only multiplying, you only have one x in there. Hence, if we think about this, about 2x as being 2x to the 1, we can apply the same logic we did to find the derivative of 5x cubed. And that is, so plus 2 times 1, because we take that exponent down, times x to the 1 minus 1, which is 0. Now our final step is we have this constant term right here. And when you take the derivative, you drop constant terms that aren't being multiplied by any independent variable. So in other words, there's no x here. 1 is not being multiplied by any x, so we just drop the 1. Now if we clean this up, we'll find that it's 5 times 3 is 15. x squared plus 2. Any number, and I'm sorry, any variable raised to the 0 power is equal to 1. So the ultimate answer is just 15x squared plus 2, which is a function that describes all of the derivatives for f of x. Hence, if I want to know the rate of change at any value of x, all I have to do is plug it right here into this function, and I'll spit out what the rate of change is. Let's go back to our plot for the function that we were looking at. Remember, it's f of x is equal to, why is there a star there? I don't know. Can I erase it? Whatever, let's keep moving. Ignore the star for just a moment. So f of x is equal to 5x cubed plus 2x plus 1. And we found that f prime of x is equal to 15x squared plus 2. Which, if we were going to graph, will look something like this. So this is f of x. And this, this is f prime x. And this is our f of x. Next, let's consider logarithmic functions. So, the logarithm allows us to think about basically, with the log, we have for some given base b, which is a constant term, we want to know what independent variable x will lead to that constant term taken to the exponent of the dependent variable y, which is really like confusing and difficult to think about. But essentially, that's why we rewrite it such that it's in terms of the dependent variable instead of the independent variable. Because basically, the original setup for a log function, it looks like it's in terms of a dependent variable, which is contradictory to the way in which we approach functions and the way in which we approach problems in economics. Remember, y is dependent on x, but it looks like we're solving for x. So we can rewrite it in terms of log, such that what we're really looking at is this right here. Now, in economics, we usually use the base of e, which is an irrational number. So whenever you see log of x, just assume I'm talking about log e of x. Now, why do we use this kind of messy, confusing functional form? Mainly, it's because we really like the shape of the function. And graphically, I think this helps show that. So in economics, we often find that this upward slope, where the rate of change is decreasing over time. So with each 1 unit increase in x, you get a unit increase in y, but that 1 unit increase in y gets smaller and smaller and smaller and smaller. And we economists find that this sort of slope actually corresponds to many different phenomena within our discipline. So that's why we actually go through the trouble of dealing with logs. Now, let's consider for a moment our motivating example, which is y, a function of x, is equal to 2 log x. That look like, so if we were going to plot f prime x right here, it would be downward sloping something like this. Again, because as we talked about before, the rate of change is decreasing over time. So this is f prime x. So we've talked about logs, we've talked about polynomials, But what about in the case where you have more than two variables? Often when we're dealing with production and utility functions, there will be two independent variables and one dependent variable. So for this utility function, right here, it's a function of x1 and x2. So we have some sort of outcome, our dependent variable, and then we have two different independent variables. So what do we do with that? Well, this is actually not as complicated as you would think. Essentially, what we want to do is we want to evaluate one variable at a time, and the variable that we're not evaluating just stays constant. In terms of notation, unlike the regular derivative, which is, as you recall, is dy over dx, the partial derivative is this fancy partial term, y over this squiggly backwards, this squiggly looking dy over this squiggly looking. Now, how do we do that? Again, if we want to evaluate, for example, we want to get to this final outcome, which is the partial derivative of utility with respect to x1. That's how we talk about this. We say with respect to a given variable when we want to distinguish that that's the one that we're taking the partial derivative of. We treat x2 as a constant. So if we're going to try to write the partial derivative of u with respect to x1, we can start out by writing that constant term, x2, to the 0.3, because we're treating it like a constant akin to 5. 5 is our other constant. We can also write 5. Now again, as we did with polynomials, what we want to do is we want to evaluate the variable that we're taking the partial derivative of and take that exponential term down and multiply the expression by that exponential term. So we add here 0.2, and similar to what we did before, now we want to take that exponential term and we want to subtract 1 from it. So we do 0.2 minus 1. So what we'll end up with is x1 to the negative 0.8. That's an 8. Not very clear. Now, when we clean all of this up, 5 times 0.2 is going to be equal to 1. So you can actually drop those. So it will be 1 times x2 to the 0.3 times x1 to the negative 0.8, which I clean up even further down here. As you can see, when we're taking the partial derivative, we're applying the same rules that we use when we're taking the derivative with two variables. We're just treating one of our three variables as a constant term. So this overview should get you going in terms of thinking about derivatives and deriving them on your own. There are other rules for derivation when you're dealing with more complicated functions. These are rules that we probably will not need for this particular class, but I'm happy to help you out with them if you're interested in learning more.